Okay, let's begin. It's raining outside, and inside we are going to study physics. I can understand your moods in such a beautiful and romantic weather. Who wants to study that also physics, all right? But it is the need of the hour, necessity of the time. So let's begin today's class. All right, my energy is a bit down today, and the class is going to run a bit long, approximately up to 11 p.m. in the night. Don't start crying that you're hungry. Let us begin the class fatapat and let us end it wrap it up fatapat also. I guess you're already seeing that what topics we are going to cover today. The last class we saw about this electric potential, right? All each and everything regarding electric potential. And I also asked before you please attend the class studying all those things. And I fully expect that you've attended the class without studying. Okay. Let us see what happens. So today, physically, we're going to study about electric field. We have already completed earlier. Last class, we talked about electric field potential. So today, we are going to see the relation between electric field and electric field potential. And after that, we'll be seeing the electric potential because of a charged sphere. All those cases. I hope you remember the sphere cases: conducting sphere, non-conducting sphere, solid sphere, hollow sphere, known as also the shell, inside, outside, surface, center, all those cases only will be seen. And no cylinder cases, only the sphere cases. So let us begin. The first topic, relation between electric field and electric potential. And also one thing, this topic is very much synonymous with gravitational field and gravitational potential. That means I mean to say that the relation between gravitational field and gravitational potential. Okay, very much synonymous topic. Okay, let's begin. The first one, relation between electric fields and electric field potential. Before beginning this topic, let me remind you one thing. If I'm having any point charge plus q at a distance of r, at a distance of r, suppose this is r. Here, the potential is given as plus kq upon r. Similarly, if I'm having a negative charge of minus q at a distance of r, the potential will be given as minus kq upon r. Right? But now say me one thing. If it is a positive charge, I hope the audio, video all are clear only. There is no requirement of asking these formalities everything. If there any kind of problem, just ask in between. So if there is a positive charge, what will be the direction of the electric field because of it? Direction of the electric field because of a positive charge is always away. And in case of a negative charge, direction of the electric field is always towards the charge. That means that direction of the electric field here is along this. And here the direction of the electric field is something along this. Now, before getting into all those things, you need to remember one thing. Just a second. Potential, I mean, electric potential always decreases in the direction of electric field. Again, electric potential always decreases in the direction of electric field. So this is a positive charge. The direction of the electric field is this way. So electric potential is going to reduce in this way. Here is a negative charge. Direction of the electric field is towards the charge. So in this case, the direction of the electric potential is going to reduce in this way again. Electric potential decreases in the direction of the electric field. Positive charge, electric field directed in this way. So electric potential will decrease in this direction. This is a negative charge, electric field directed in this way. So so potential will decrease in this way. Okay, let us see how it is happening and why it is happening. Let me consider here 3 points. Let this point be A, B, and C. Let this distance be suppose 1 centimeter. Let B be at a distance of 2 centimeter, and let C be at a distance of 3 centimeter. Barabar? Similarly, this point be A, this point be B, and this point be C. Here also, A is lying at a distance of 1 centimeter, B is lying at a distance of 2 centimeter, and C is lying at a distance of 3 centimeter. Tell me one thing, what will be the potential at this point A? The positive case, VA will be KQ upon, what is the value of R1? VB will be KQ upon, what is the value of this one? R is 2 now. What is the value of potential at this point C? KQ at C, the distance is 3 centimeter. Right? Say me one thing. Who is greater and who is small? If the denominator is greater, the term becomes small. Denominator is smaller, the terms become greater. Something divided by denominator. Suppose you are dividing 10 by 5, answer is 2. You're dividing 10 by 10, answer is 1. You're dividing 10 by 100, answer is in decimal. So the more the denominator increases, more the value, more the denominator is, less is the value. More the denominator is, less is the value. Less the denominator is, more is the value. Obviously here, VA greater than VB greater than VC. Clear now? Who is having the highest potential here? VA is having the highest potential. And VC will have the lowest potential because the denominator is greater. Consider na K cube as 100. So what will be VA? 100 by 1 is equal to 100. What will be VB? 100 by 2 is equal to 50. What will be VC? 100 by 3 is equal to 33.33. So who is greater? VA greater than VB greater than VC. That means what? VC is the smallest one. What we told. Electric field potential decreases in the direction of the electric field. For the positive charge, this is the direction of the electric field. So electric field potential decreasing, VC less, VA more, VA greater than VB greater than VC, all clear. Let's talk about this one. Let's talk about this one. What will be the potential at A point? Here potential at A will be minus KQ upon 1. Potential needs to be put on the sign. VB will be minus KQ for B, distance is 2. And VC will be minus KQ upon this distance 3. Now say me here, who is greater, who is less? कौन बड़ा कौन छोटा एक चीज बताओ, who is greater, -5 या -10? Who is big and who is small? Obviously -5 is bigger than -10. है कि ना? -1 is greater than -3, 0 greater than -1, right? So tell me one thing, in these 3 cases, who will be the greater? VA will be smaller, VC will be greater. Akina, VA will be smaller, VB will be greater than VT, VC will be greater than V3. Whatever happens in positive, in case of the negative things, the reverse thing happens. Whatever happens in positive, in case of negative, the reverse thing happens. Now, this is the easiest way to understand. You apply some in class 12. I hope you understand that much. Okay, fine. Let us consider again. Let K cube is equal to 100. So VA will be minus 100 by 1 is equal to minus 100. So VB is equal to minus 100 by 2 is equal to minus 50. And VC is equal to minus 100 by 3. Let me change the marker. It is not working. VC will be minus 33. Now, tell me who is greater? Minus 100, minus 50, minus 33. Obviously, minus 33 greater than minus 50 greater than minus 100. What is minus 33? V at C greater than V at B greater than V at A. Okay, no? So this is greater. VC is greater. VB is smaller than VB is smaller than VC, and VA is smaller of all. That means what? The potential is decreasing in this way. VC is the highest. VB is less than VC, and VA is the smallest of all. Potential is decreasing in this way. This is the direction of the electric field. Potential decreasing in this direction of the electric field. Your potential was decreasing in this direction. Your potential decreasing in this direction. That means what? Potential always electric field's potential always decrease. In the direction of the electric field. Electric field potential always decrease in the direction of the electric field. Clear this much? I hope it is. Now we are going to establish a relation in between this electric field potential and the electric field. Okay, let us see. Okay, I'm rubbing it here. Relation between electric field potential and electric field. Now, say we have one thing, electric field can be of two types. One is an uniform electric field, the other one is a non-uniform electric field. So electric field potential can have one kind of relation with a uniform electric field. Electric field potential will have different kind of relation with non-uniform electric field. Let us see what is going to happen. Initially, we'll be talking about the relation between electric field and electric field potential. Which electric field? Uniform electric field. So relation between uniform electric field and field potential. Okay, uniform. Let us consider an uniform electric field. Let us consider a uniform electric field. Uniform electric field. Okay. In this field, let us consider a point A and another point B. Let the position vector of A be R1. Let the position vector of B point B R2 vector. In Cartesian fields or in physics, any location, any point, we denote by what? Position vector. Now, what is position vector? The class 11th में पढ़े थे. Position vector. Vector is always plotted in the Cartesian plane, means graph paper. So let this be the axis. X-axis, y-axis, this is the origin. Let this point be A. Let the distance of this point A from the origin be R1. I'm talking in very simple terms. I'm not getting into the details of the position vector, displacement vector, and all. The basic things you need to understand: what is position vector and what is displacement vector. Those who remember this one point, those who do not remember the maximum ones, look at it. So let the distance of this point A from the origin be R1. Let us talk about the displacement. What should be your displacement if you start from origin and travel to A? Displacement is a vector thing, it will be R1 vector, right? Let another point be B. So what will be your displacement if you start traveling from the origin and travel to B? Let it be R2 vector, right? Let it be R2 vector. So R1 vector is the position vector of this point A, and R2 vector is the position vector of this point B. Now, if you ask me what is the distance between A and B, or what would be my displacement if I start traveling from A and reach at B? A is my initial point, B is my final point. I'm traveling from A to B, I'm having some displacement. This displacement is given by displacement vector. And the displacement vector between A and B is given as R2 vector minus R1 vector. Now let it be equal to delta R vector. Anything difference between any two terms in physics we represent with delta, no? In physics or maths, difference between any two things is delta. Initial velocity minus final velocity is equal to delta velocity. So R2 vector minus R1 vector will be delta R vector. So this delta R vector is the displacement vector of A and B, or displacement vector of B with respect to where? Displacement vector of a B with respect to A is equal to delta R vector, and delta R vector is equal to R2 vector minus R1 vector. Now, how delta R vector is equal to R2 minus R1 vector? I'm not going into these details. You can also see, if you remember, this is the triangle law and all. Okay, now let us leave all those things. Let's stick to the topic. And displacement vector of B with respect to is delta R vector. Delta R vector is what? R2 vector minus R1 vector. Then let us consider its magnitude. Let us consider its magnitude. The modulus of delta R vector be R. Let us consider the magnitude is equal to simple R. Okay. So this is my A, this is my B. Position vector of A is R1 vector, position vector of B is R2 vector. This is the displacement vector, delta R. The magnitude is this much length value, is smaller, and the whole is displacement vector. At A, I'll be placing a test charge. What is a test charge? Small positive charge. Suppose plus Q. What is plus Q? Plus Q is a test charge. That means what? Limit Q tends to 0, because it is a test charge. Okay. What is my motive? My motive is to find the relation between uniform electric field and field potential. So I need to find out the electric field potential first. Electric field, so I know what will be. Take you up an arch for whatever it is. I need to calculate the electric field potential. I'm just calculating the electric field potential. Okay. So if I am asked what will be the potential difference between these 2 points, what to do to calculate the potential difference between any 2 points? From the initial point, take a very small charge very slowly to the final point and calculate the work done per unit charge. The work done by whom? The external agent. Already discussed about these things. So from at A, I am placing a very test charge, class A. I'll be taking this test charge from A to B very slowly. So that there is no change in the kinetic energy of the system. No change in the kinetic energy of the charge. Now say me one thing. The moment I'm placing this plus Q in this electric field, whenever there is a charge in a field, the charge experiences a force. The magnitude of the force is given as Q into E. What is the direction of that force? If it is a positive charge, the direction of the force is in the direction of the field. If it is a positive charge, that means what? It will experience a force in this way. What force it will experience? An electrostatic force it will experience in this way, in the form of Q into V. Happy na? Whenever you are keeping a positive charge or negative charge, the charge experiences a force. If it is a positive charge, the charge will experience a force in the direction of the field. What is the field? Capitally, what is the charge Q? So this will experience a force of Q into V direction along the electric field, because this is a positive one. So this force Q into E, this force Q into V, this force Q into V will now try to pull it along the electric field. Taken. You kept this charge very much at rest. Because of this field, it is having a force of Q into V. This QV will try to push the charge in this way, and gradually the charge will start accelerating. Acceleration means change in velocity. So Q will have a change in velocity. But our target is to keep the kinetic energy constant. To keep the kinetic energy constant, half mv square, we cannot let V to change. But this QV will let its V to change, its V to increase or decrease or whatever it is. This QV will let this Q will lead in this acceleration, because whenever force is equal to mass into acceleration. So whenever a mass is kept, whenever a mass is having a force, it will face an acceleration. This is a charged body. Charged body has some mass. The charged body is facing a force of Q into V. It will accelerate in this direction. If it is accelerating in this direction, it will experience a change in velocity, but which we cannot let. So to stop its acceleration in this side, what we need to do? We need to apply an external force in the opposite direction. And this way. What happens in that? What happens in that? Suppose this electrostatic force is 10 Newton, will be applying a force externally, for example, 9.99999999 Newton. So in this side, there will be very much negligible force. With this negligible force, the charge will not travel to either, but it will face no acceleration and no change in velocity. Our kinetic energy will now stay constant. We place this charge either. It is having a force Q into V in this direction. This force will accelerate the charge in this way. Acceleration means change in velocity. We cannot let velocity to change because our target is to keep the kinetic energy constant. To keep kinetic energy constant, our V cannot change because kinetic energy is equal to half mv square. Our V cannot change. So to stop the charge from accelerating in that side, what we did is that we applied an external force in the opposite direction whose value is almost equal to the force in that direction. If this is some 10 Newton, this value is some 9.999999999 Newton. Such that there is a very negligible force in this direction. This negligible force will now take this charge from A to B. As the force is very much negligible, see, force is very much negligible, 0.10 Newton, 9.99999999 Newton. What is the force? 0.111111 in this direction, almost equivalent to 0. If the force is almost equivalent to 0, acceleration is what? 0. If acceleration is 0, this is now having no change in velocity. No change in velocity means our kinetic energy constant, our criteria fulfilled. Already cleared your last class, this class also. So what we are doing is that we are applying an external force in the opposite direction, and this external force, these values in physics, we say that they are almost equal only. So we say that F external is equal to F electrostatics. And as because they are vectors, the directions are opposite, we put this minus sign. Clear? And what is the value of this electrostatic force? Negative Q into V. Minus the sign of the direction. Now say me one thing. What is the how to calculate electric field? Sorry, potential difference. potential difference is always calculated as the difference in potential between the final minus initial. Which is your final point? This one. This is your initial point because you're traveling from here and reaching over B. So electric field, electric potential difference V final minus V initial is equal to work done by external from initial to final per unit charge. So at the final point is B and the initial point is A. Work done by external from A to B divided by B. And VB minus the VI, you can write delta V, potential difference, is equal to work done by external from A to B divided by Q. This much we know. This much we know. So to calculate the potential difference between A and B, we now need to calculate the work done by the external force from taking this charge from A to B. So what is work done? Work done is equal to force dot displacement. What is the force here? Work done by which force? We are talking about the work done by the external force. What is the external force? Minus Q into B. Minus Q into E vector. What is displacement? This is the displacement. What is the displacement vector? Delta R vector. So this is the work done by the external force in taking the charge from A to B. Substitute this value here. We'll be having delta V is equal to what is the work done? Minus Q. Minus Q E vector delta R vector divided by Q. Q will cancel out each other. So we have potential difference is equal to minus E vector dot delta R vector. This is our electric field E, uniform electric field E, electric potential between 2 points in this electric field, electric potential between A and B in this uniform electric field E. So this is the relation between uniform electric field and electric field potential between 2 points in that field. Delta V is equal to minus E vector dot delta R vector. Clear? This is the case of uniform electric field and field potential relation. Clear? Acha, say me one thing. We are always saying that there is no change in. We are always saying that we cannot allow the change in the kinetic energy of the charge that we are taking from either to either. We cannot allow the change in the kinetic energy. Why? What will happen if the kinetic energy changes? Try to keep the velocity constant. What's a velocity? I mean speed constant, so that we do not alter the kinetic energy. Okay, but why you cannot alter the kinetic energy? Why you do not like altering the kinetic energy? The reason is that we are dealing with the work done in between 2 potentials. So obviously this work done is always related to energy. More the energy, more is the work done, less the energy, less is the work done, no energy, no work done, simple thing. So work done is always related to energy. Here we are calculating work done between 2 potentials in a potential field. So here the work is done by the energy called potential energy. So here the entire work done is related to the form of energy will be potential energy. Now, so it means what? We're calculating potential difference by means of work done. Work done by whom? Potential energy. So to calculate electric potential difference or electric potential, we need work done by potential energy. That much is clear, right? This work is done by whom? Potential energy. We are calculating work done between A and B. Who is the force related? Electrostatic force, or its opposite, external force. Who is the energy related? Potential energy is related. In the next class, we'll be talking about that only, electrostatic potential energy. Now, tell me one thing. If I change the speed of the charge, its velocity will change. I mean, its kinetic energy will change, because kinetic energy half mv square. If you change v, kinetic energy is going to change. Now, if kinetic energy develops in the body, where from this energy will come? By conservation of energy, energy is always constant. If the entire system is having an energy of 100 joule, after 5 hours also it will have an energy of 100 joule only. In between, if I change the kinetic energy, for example, I increase the kinetic energy, we are from beginning from either to either. If I increase the kinetic energy, the kinetic energy is not going to come from somewhere else. Part of the potential energy will get converted to the kinetic energy. For example, out of this 100 joule, 20 joule was converted into kinetic. Now potential energy is what? 80 joule. But to calculate this work done, to calculate the electric potential difference, to calculate the work done, I need what? Only and only potential energy. What was earlier, and now right now also I need the same potential energy. That means what? I cannot afford converting a single part of the potential energy into the kinetic energy. I cannot afford that. That is the reason we do not alter the kinetic energy of the system or the charge of the body or whatever thing, such that the entire energy stays in the form of potential energy, which will be referring to calculate the work done such that, so that we can calculate the potential difference of electric field potential. Clear? Search in the books, you will not get the answer. So keep that in mind. I'll be getting into the second case, relation between non-uniform electric fields and field potential. Okay, non-uniform electric field and field potential. So few of the things be there. Relation between non-uniform electric. Relation between non-uniform electric field. So let me try to draw the non-uniform electric field, something like that. Okay. Just it is a diagrammatic representation. It is not a standard one, because you know the non-uniform electric field is created by whom? By a point charge. And the uniform electric field, where we get uniform electric field? Where we are having uniform positive, uniform negative electric field lines from positive to negative, uniformly separated, parallel to each other. Uniform electric field found where? In between the capacitor plates. And non-uniform electric field is formed by a point charge. Electric field lines are radially outward. Non-uniform electric field. Okay. So let this be non-uniform electric field. In this non-uniform electric field, we are taking 2 points A and B. Position vector of A is R1 vector. Position vector of B is R2 vector. The displacement of B, displacement vector of B with respect to delta R vector. R2 vector minus R1 vector will be given as delta R vector. All the things are all same. Just to change the electric field from uniform to non-uniform. Let this non-uniform electric field be E. Our target is same. We are taking a test charge plus Q at A. We'll be taking from A to B. We'll calculate the work done. By that, we'll be finding the electric potential difference between A and B. And finally, we'll derive a relation between this electric potential and electric field. Okay, let us see how to do. Let us see how to. Say me one thing. Finally, what we'll get? VB minus initial. In the last case, what we got? VB minus VA. In the last case, what we got? VB minus VA is equal to minus E dot net. Again, that is the thing we got now. Delta V is equal to minus E vector dot delta R vector. That is the thing we got in case of uniform field. But now, I cannot use this delta R. I cannot now use this distance as delta Ry. This distribution vector is still now delta R only, but I cannot use it now. I cannot use this expression now. Why? Because this earlier, along this distance, along the entire scale, along the entire distance, electric field was uniform. What the field was here, the same field is here, same field is here, same field is here, same field is everywhere. Now, at different point, we'll be having different electric field. Okay, now what is uniform electric field? What is non-uniform electric field? Non-uniform electric field is always because of a point charge. It has given us what? KQ upon R square. So the distance changes, the field value changes. This is the distance, something value. Distance changes, some other value. Distance changes, some other value. That means what? I cannot take the entire distance as only and only R or delta R. So what I need to use? I will be now taking a very small portion of this delta R or R. The magnitude of delta is only smaller. I'll be taking a very small portion of this delta, and I'll be saying that let its length be dr, very small, infinite small elementary portion from our delta R vector be dr vector. I'll be now talking about the electric field for this dr. Okay, say now one thing. The value of electric field for value for non-uniform electric field in this point, in this point, in this point, and this point are all different. Now let us consider this is our dr. Dr is a very infinite small area, infinite small length. Let this be dr. Now in this small dr, field will be uniform now. Let me consider this hand. My body is made up of trillions of cells. What is the number of cells in my hand? Suppose 100. What is the number of cells in my face? Suppose it is 200. Number of cells in my this hand? Suppose 300. But in a very much small area, throughout my body, everywhere the number of cells will be what? Same only. Maybe the number of cells is different here and different here. But if I take a very small portion of my body, here the number of cells will be equal to the number of cells here only. For a small length dr, the value of the electric field E will be the value of electric field will be same here, irrespective of the non-uniform electric field here and here. The electric field is non-uniform throughout the surface. But for a small area, electric field will be what? Constant. Here electric field 10, 12, 14, 15, 16, 17, 18. But a small area, it is 10. 12 for a small area, it is 12 constant, right? So for a dr length, electric field will be what? Constant. Clear this much? For a dr length, electric field will be what? Constant. Now say me one thing. This was the potential difference for delta R length. So for a dr length, we'll be having a very small potential difference, dV. Okay, now. If for the total length you are having, in case of the uniform one, delta V. So for a small length dr, we'll be having a very small potential difference dV, and it will be given as what? dV is equal to minus E dot dr. Okay. Come again. This was the case for uniform electric field. Now what I'm saying that right now from A to B, all the different points, electric field is different. So I cannot use this thing. This could be used when electric field is uniform everywhere. Now I need to calculate potential difference for small part. Then I'll be summing all those potential differences. With the help of integration, I'll be getting the total potential difference. Because the electric field is non-uniform. So I chose out of this dr, out of this R, a very small elementary length dr. The electric field can be uniform, non-uniform everywhere, but for a small part, for a small area, for a small length, electric field will be uniform only. So for this dr length, for this small dr length, we'll be having a small potential difference. And for this dr length, electric field is what? Uniform. For a small part, electric field is uniform. So for this dr length, the potential difference will be given by the concept of uniform electric field. Uniform electric field is delta V is equal to E dot delta R. So for this small dr length, small potential will be dV. Electric field will be uniform for this small length. And in place of delta, we'll be writing just that dr because we're considering the small length only dr. Clear? So this is the small potential difference generated along this length dr. If you take another dr, we'll be having another dV is equal to minus E dot dr. So along this entire length of AB, will be having infinite size small dV, and dV. How to calculate? Integrate. Whatever. So this is the small potential. So the entire potential difference between A to B will be given as V is equal to integration of dV is equal to integration of minus E dot dr. Now to integrate, we need the limits. What should be the limit? Lower limit is where from you are starting. From A you are starting. Higher limit is where you are reaching. You are reaching at B. The limit should be what? A to B. A to B. A to B. This is the relation between non-uniform electric field and electric field potential between 2 points A and B kept in this non-uniform electric field. Is this concept clear how we did? For uniform electric field, everywhere field is uniform. We got the relation delta V is equal to minus E dot delta R. Now from A to B, a field is not uniform. At different points, we're having different field value. Some are distant, 12, 13, 14, whatever and whatever. So dr is a very small length. At this small length, the field value will be constant. And for a constant field along this length dr, we'll be having a very small potential difference at dV, which will be given by the concept of this concept, uniform field. So dV will be equal to minus E dot dr. Now from A to B, we'll be having infinite cells at dr, infinite cells, small dV. We'll be integrating and we'll be calculating the total field, total potential difference between A and B. Limit should be from where you are beginning, where you are ending, lower limit, higher limit, A to B. That is the thing. Clear? So this is the case of uniform. This is the case of non-uniform. Relation between electric field and electric field potential in when the fields are either uniform as well as non. Clear? Okay. Now the thing is that we can apply this case, we can apply this formula, this expression to calculate our relation in the uniform case also. This is particularly in the uniform case, this is particularly in the non-uniform case, but we can use this expression to calculate the relation between electric field and electric potential in the uniform case also by using this one. We can derive this one also by using this one. Let us see. We'll be landing over here by using this one. Let us see. I'm having these things are not more needed. Let me wrap this one also at 40 seconds. Okay. What I told is that by using the expression we derived in the non-uniform case, we can land upon the expression we are having in the uniform case also. Let us use this one. What I have in integration delta V, sorry, dV from A to B is equal to integration minus E dot dr from A to B. That is the thing we are having. We need to reach here. Tell me one thing. If we integrate a dv, integration dv will give us what? V. Take this minus sign outside. Take this minus one outside. We'll be leaving behind with what? E dot dr. Again. Now, what is E dot dr? E dot dr is E dr cos theta. A dot B is AB cos theta. I'm sorry. Okay. Put the limits of B and A. It will be VB minus V. What is your E? E is uniform. We are talking of deriving what? We are talking of deriving the relation when the field is uniform. So E will be coming out. What is cos theta? Cos theta is also a constant. It will be coming out. And what will we have in dr? Right. What will give us integration of all dr? Integration of dr will give us what? Dr will give us what? Smaller. Okay, what it told? R2 vector minus R1 vector is equal to delta R vector. And let us consider the magnitude of R2 minus R1 vector as R. That means what? The magnitude of delta R vector is also R, na? If the magnitude of this one is R, the magnitude of this one is also R only, na? This is magnitude you're taking as R. This is equal to this. So this magnitude also what? R only. So can I write integration of dr will give me what? R. Integration of dr will give me what? R. Okay, I'm writing R only. VB minus VA is delta V minus E cos theta. It will be RB minus RA. RB minus RA. So that case we took B and A, right? We took B and A, right? So what is the value of RB minus R? What is the value of RB minus RA? Delta. What is the value of RB minus RA by? Okay, fine, it is R only. Keep it as R. And what is the magnitude of R and delta are the same in thing, na? R and delta are the same thing, na? R, I took the magnitude of this one. So if the magnitude of this one is R, this is equal to this magnitude also what? I can write in place of R delta. Yeah, I can write in this form minus E delta R cos theta. Now what is AB cos theta? AB cos theta can be written as A vector dot B vector. So E delta cos theta can be written as minus E vector dot delta R vector. This was the case of the non-uniform, but derived the uniform case also. This means what? This you can apply anywhere, anytime. Field can be uniform, yeah, non-uniform. You can apply this one. Field may be uniform or uniform. Any case, any example, any solution, any numerical. You're not finding the field is uniform or not uniform. You're having a doubt. Field uniform and non-uniform. No doubt of any kind of doubt. Use this one. If the field is uniform, your answer will come. If the field is non-uniform, your answer is still going to come. No need to land up in any kind of confusion. And if strictly know the field is uniform, use this one. Simple. Clear? This is all about the relation between electric field uniform or in non-uniform with electric field potential. So V is equal to negative E dot di. Bas, खत्म. Single relation. Relation between electric fields and potential. This. Use it anywhere. Use it anywhere. Just don't forget to put the limits here. Clear? Now tell me one thing. If any question, E is given, you can easily calculate V. dRVR is given, E is given, you can calculate V. Field is given, you can calculate potential. Field is given, potential calculation now you can do. What if they give you the potential and ask to find the field? Field is given, E is given, we can calculate potential now. Obviously, we'll be seeing examples. What if now, if field is given, V is given, they'll be asking to calculate E. What will you do? Cross multiplication. There is some integration, dot product. You cannot do this, bring this side change. Now, tell me one thing. We already know these things. We have spoken so many times that in physics, the concept of differentiation and integration. If we integrate something and if we are integrating something and we are having the result. Now, if we differentiate the result, okay, let me speak it in a more easy way. If I differentiate velocity, I get acceleration. dv dt is equal to V. Now, if I integrate acceleration, I get velocity. Whatever thing we are getting by integrating, if we differentiate the same thing, we get the reverse thing. Let's say an example. Acceleration is what? dv dt. We are differentiating velocity with respect to time or whatever, and we are having acceleration. So cannot do that like that. dv is equal to a dt. Put an integration sign. Integration of all dv will be what? Velocity is equal to integration a dt. So what we did is that we differentiated v to get acceleration. We differentiated the v to get acceleration. And here we integrated acceleration to get velocity. We integrated acceleration to get velocity. We differentiate something, we get a result. The result, if we integrate, we get the same thing, the old thing. We differentiated velocity, got acceleration. We integrated acceleration, got velocity. Now, say me one thing. We are having v is equal to minus e dot dr. Okay. What was the earlier step? For a small dv is equal to minus e dot dr. This was the earlier step. No? Now you can say by differentiating, see, by integrating e, we are getting v. By integrating e, we are getting v. So if we differentiate v, we'll be getting by integrating v, by integrating a, we get v. So by differentiating v, we get a. By integrating e, we get v. So by differentiating v, we'll be getting e. That much thing is clicking. By differentiating v, we'll be getting. Is it visible? That is very much visible. Clear now? By integrating A, we got V. And by differentiating V, we got A. So here, by integrating E, we got V. So it's a matter of common sense. By differentiating V, we'll get E. But we cannot do that here. We cannot do that here. We cannot write like that. That by integrating E, we got V. By differentiating V, we'll get dr dV upon dr is equal to minus E. E is equal to minus dV upon dr. We cannot do these things. Why cannot we do these things here? These things are correct in physics. So why cannot do these things? By differentiating V, we're getting E. By integrating E, we're getting V. Maths is saying we are correct, but this is wrong. Why? Here, E and dr is connected by a dot. They are connected by a dot product. That means what we'll be having here minus E dr cos theta. So in this expression, what is cos theta? Huh? Mathematically wrong. Mathematically wrong. By integrating something, we definitely get the product. By integrating something, whatever we get, by differentiating the same thing, we get the earlier thing. That is true. But here, they are connected with a dot product. We're having some cos theta in between them. So we cannot do it over here. Clear enough? Katra kahan pe? So let us now learn. E is given, V can be calculated. If V is given, how to calculate E? Let us take this topic very much seriously. Hundreds of questions and numericals have come in any sort of exam, school exam, board exam, NEET exam, JEE exam, whatever the exam is. It came between E and V. E will be given calculate V, V will be given calculate E. Take it very much seriously, okay? So those who are browsing, please be serious. Let us now understand if V is given, how to calculate E. What is E? E is electric field. E is electric field vector. E is electric field vector. It can be in all the three directions. If I want to write it in the component form, in the vector form, what it will be? E x I cap plus E y j cap plus E z k cap. This will be the thing now. We want to write E in the all these three directions in the vector form. E is equal to Ex I cap, Ey j cap, Ez k cap. Right? What was our displacement vector? Delta R vector or R vector. So how to write R vector in the vector form? Those who have forgotten, please remind it. It will be X I cap plus Y j cap plus Z k cap. Displacement can be in all these three directions, X, Y, Z, along X, X, I cap, along Y, Y, Z, K, along Z, Z, K cap. And electric field in along three directions, Ex, I cap, Ey, J cap, Ez, K cap. This is the way to represent a vector in all these three directions. Electric field vector, displacement vector. I need dr vector. So to calculate dr vector from this, I need to do partial differentiation. I need to do partial differentiation. I cannot do complete differentiation because there are different variables. I can do, and what I'll be doing is that partial differentiation. So if you partially differentiate it, we'll be having dr vector is equal to dx I cap plus dy j cap plus dz k cap. If you are not revising class 11, obviously some things will go above your head. What can I do? कितनी बार कराओ यार? इतना ही है. Electric field resolved into three directions, X, Y, Z. Displacement vector resolved in three directions, X, Y, Z. In this way, you need to write, keep it in mind every time. We will need it many places. Then partially differentiating, we're having dx I cap, dy j cap, dz k cap. What is V? What is V? You're having now dv is equal to minus E dot dr, right? Small potential. So for dv, can we write dv is equal to minus E minus E x I cap plus E y j cap plus E z k cap dot dr vector is this one, dx I cap plus dy j cap plus dz k cap. It is a dot product. How to do dot product? I with I, j with j, k with k. So what will be having? We'll be having ex dx, and I dot I is 1. Now this one with this one, it will be e y dy. J dot j is 1 plus e z dz. This is where we have landed till now. Minus minus करना तो कर लो. dv is equal to minus ex dx plus, sorry, minus ey dy minus ez dz. We have landed up to here. Okay. Now what will be doing? Now we'll be partially differentiating this expression again. We'll be partially differentiating this expression once with respect to x, then with respect to y, then with respect to z. We'll be again partially differentiating this one. dv is equal to minus ex dx minus ey dy and minus ez dz. We'll partially differentiating. We'll partially differentiating first with x, with respect to x, with respect to y, then with respect to z. So before getting into partial differentiation, always keep in mind, when you will be differentiating with respect to x, the other variables will behave as constant. When you will be partially differentiating with respect to y, the other variables x and z will behave like constant. When you will be partially differentiating with respect to z, the other variables x and y will behave like constant. Okay. So first of all, we'll be doing partial differentiation with respect to x. And the symbol is written something like this. It is also called del. It is also called del. So we are partially differentiating this expression with respect to x. Will be getting what? Del v del x is equal to partial differentiation of minus ex dx. Will be giving us what? Minus ex. Partial differentiation of minus ex dx will be giving us what? Minus ex. So where is the dx gone? Okay, see. Let me show the process. It will be what? We are partially differentiating this one with respect to x. So dv dx will be saying like that, del v del x is equal to del this is the thing now. We'll be having what? Minus ex, and dx and del x will cancel out each other. Dx and del x will be cancelling out each other. This is the way. So del v del x is equal to negative of ex. That means what? We can write what? E along x is equal to minus del v del x. This is called potential gradient. This is called potential gradient. Also see from this expression. along the direction of the electric field, potential is what? Decreasing. Along the direction of electric field, potential is what? Decreasing. It is coming as negative. Clear? So this is Ex, that is the electric field along the X. Now I'll be differentiating this one with partially differentiating this one with respect to Y. So what will be having now? Okay, we are partially differentiating this one. This will appear as what? Constant. Constant differentiation is 0 only. Now partially differentiating with respect to Y, del V del Y. This will behave like a constant, will be having 0. This will become what? Minus Ey d will be only minus Ey. The same way, minus Ex dx become minus Ex. And this one also behave like a constant, so 0. So ultimately I'll be having what? E along Y is equal to minus del V del Y. And similarly, we can say that E along Z will be what? Minus del V del Z. Again, one will be partially differentiating with respect to Z. X and Y terms will appear as constant, 0, 0. And this will be minus Ez. Clear? Okay. I hope this much is clear. Okay. So how to write now E? So what is our E? E is equal to Ex I cap. What is the value of Ex? Value of Ex is minus del V dx. So we can write that E vector is equal to Ex. Ex is what? Minus del V del x I cap plus Ey j cap. Value of Ey is minus del V d del y and j cap plus Ez. Value of Ez is minus del V del z. Plus minus a minus del V del z and k cap. This is the value of the electric field vector. This is the value of the electric field vector in the vector form. What will be its magnitude? Magnitude will be what will be the magnitude? This square plus this square plus this square root minus del V del x square plus minus del V del y square plus minus del V del z square root. That is what? The magnitude of the electric field will be given as del V upon del x square plus del V upon del y square plus del V upon del z square. This is electric field magnitude. My marker is betraying me today. Is it visible? Yeah, it is visible. What was our motive? What was our motive? I'm adding it here. Having V is equal to minus E dot dr. What was our motive? Our motive was, I asked that, now if E is given, you can calculate V. What if V is given, how to calculate E? See, E has been calculated. E has been calculated. Clear? Remember this, remember the steps. We'll be seeing the examples today only. I'll be showing you one example, and these things will become more clear. Remember these techniques, remember these steps. This is the E along the X, this is the E along the Y, this is the E along the Z. They're called potential gradient. I'll come to potential gradient in this chapter in some next class, maybe. So E along the E in the vector form is something like that. R along the vector form is that. Dr vector is written like that. So this is the magnitude. Sorry, this is the electric field which we have derived in the vector form. This is the magnitude of the electric field. You have nothing to do. You have to remember these steps. Also, you have to remember this expression. Also, there is no escapism because one question, 95% confirm. It will come. It is going to come. And whatever exams you are going to give, in any of the exam, at least one time, one question will be having. Either you will be given calculate B. You will be given calculate B. B will be given calculate E. L no E. In vector form, in magnitude form. Clear? Okay. Yeah, it's a beautiful one. I know. Physics, everything is beautiful. Everything is interesting. The ones whose mouths are still hard, close it. So we took two goals to study today. One was relation between electric field and electric field potential. The other was the sphere cases. The first goal is complete. Relation between electric field and electric potential. Everything has been completed. You don't need to study anything else. Okay. Let's take a study from the books here and there. Doesn't matter. Now let's get to the second goal. The sphere cases. Electric field potential at different places due to different type of charged sphere. Okay. So how many types of sphere? Let us begin the English class. S-P-H-E-R-E, sphere. A sphere can be made up of conducting material. Sphere can be made up of non-conducting. That will be not using non-conducting, we'll be using dielectric because we're in physics class. Right. The conducting one can be solid. The conducting one can be hollow. That will be same shell. Similarly, the dielectric one can be solid. The dielectric one can be shell. In all those places, we'll be seeing outside, surface, inside, and center. Okay, now we know that solid shell, dielectric shell cases are same to same. Okay, because whenever you are giving a charge to a sphere, let us talk about a conducting sphere. Be it hollow, like in shell, be it solid, charge resides on the surface. Same case. Also, we know that if you are giving some charge to a non-conducting hollow sphere, that is a dielectric shell, charge goes to the surface. So this will be same case. This one always creates a jhamela, non-conducting solid one. Okay, let's begin. So we will be picking this topic, conducting solid shell or dielectric shell. This one, let's begin. I hope no one is falling asleep. What is the time? Are we running out of time? Oh God, no. There is plenty of time. Puri raat pari hai yaar. Nobody's having exam tomorrow. No one is having exam tomorrow. So we're talking about solid, hollow, conducting, and hollow, non-conducting. Hollow non-conducting means dielectric shell. Let us see. Outside, then surface, then inside, then center. Clear enough why we're wrapping up in this way? Because a solid conducting solid, a solid conducting and a hollow conducting behaves in the same way. You give the charge, charge gets on the surface. Potential happens because of charge. So for potential to be potential, it doesn't mind the sphere was hollow or solid. It just sees that it is a conducting sphere. I'll go to the surface. The cases will be same. Now we already know this thing that for a non-conducting hollow sphere, that is a dielectric shell, it also behaves the same way. Charge resides on the surface. Only in the case of a non-conducting solid sphere, that is a dielectric solid sphere. Only in the case of a dielectric solid sphere, the charge resides in the volume, right? Okay, let us see. So let's consider the sphere. This is a sphere. It's a beautiful thing. Just concentrate. Let the radius of the sphere be capital R. And we have given some charge. Let the charge be plus Q. Let the charge be plus Q. Just a second. Okay. Somebody left the class and has entered again. So this thing is clear why you are wrapping up in this way. Because a solid or hollow conducting and a hollow and conducting behave the same way. So we take a sphere. What kind of sphere? It can be a solid conducting, it can be a hollow conducting, it can be a hollow non-conducting, whatever that is. You're taking a sphere. And the radius of the sphere be capital R. We are giving it some charge positive Q. We're talking about the outside point. Distance is always calculated from the center. Let the distance be R. So obviously for outside case, small r greater than R. This is the point. Let this point be P. We are going to calculate the electric field potential at this point P because of this charged sphere. First, see the actual process. After that, I'll give a short trick. You have to calculate the electric field potential at P. Now, say me one thing. Potentials are not defined. Electric field potential cannot be defined in physics. What is defined is potential difference. Now, to calculate potential difference, we need 2 points, VA, VV. One point is already there, P, where we need to calculate. We need another point as the reference point, because until and unless you're having 2 points, you cannot calculate the potential difference. Again, for calculating potential, things are not defined. What is defined is potential difference. For calculating potential difference means what? Calculating difference in potential in two different points. For that, we need 2 points. 1 point would have been P. Another point we also need. Which point to take? Let us take infinity. Let us take infinity. Why infinity? Because ultimately we are asked to find out the potential at P. So what will we be doing? We'll be taking a positive charge, test charge from infinity, and we'll be bringing it over here. And the potential difference will be Bp minus V infinity is equal to some work done upon the charge. Now V infinity will be 0. V infinity will be 0. So in this way, I can calculate the potential at P. This is the way now how we used to calculate the particular potential at a particular point. We used to take the reference point as infinity because there it is already 0. It is an assumption. In the last class, I've already proved how infinity potential is 0. Right? So we take the reference point as infinity. And from infinity, we'll be bringing a small test charge from infinity to P. How? So that there is no change in the kinetic energy of the charge. And we'll see the work done in the entire process. And what is the work done per unit charge? That will be the potential difference between A and A. And this is already 0. So we'll be having potential at P as some work done upon Q. All our old friends, right? Okay. Now say me one thing. At this point P, if I talk about the electric field, what is the electric field at P? Electric field outside is PR is given as E is equal to KQ upon R square. KQ upon small r square. Small r is a variable distance. So electric field at P will be variable, right? So if I want to write the relation between V and E at P, I'll be taking into consideration the case of relation between non-uniform electric field and potential at P. So for P, I can write V is equal to minus integration E dot dr. Can I write? Because number one case electric field either is non-uniform. KQ upon R square, R is variable. Another thing is that we can use this formula anywhere. Be the field uniform, be the field non-uniform, doesn't matter. I'm taking this one. V is equal to E dot dr. Okay, not V actually, delta V is equal to E dot dr. Again, potential difference is equal to minus integration E dot dr. What is potential difference? Potential difference is final point potential minus initial point potential is equal to. Barabar. What is the final point? We are talking about P. What is the initial point? We'll begin our journey from infinity. Which E we are talking about? Electric field at P we are talking about. What is the electric field at P? Electric field at P. Electric field outside the sphere given as KQ upon distance square. Right? So Vp minus 0 is equal to minus, it will be KQ upon R square dot dr. Okay, let me write this down later on. इसको अभी नहीं लिखते. Now, say me one thing. E dot dr will give us what? E dot dr will give us E dr cos theta. What is cos theta? Theta is the angle between E and dr. What is the direction of E? Direction of E will be like that, in this way. Again, because direction of electric field is always away from the positive charge. And what will be the direction of dr? Distance always from the center. The direction of dr will be also in this way. Dr. So E and dr are directed in the same way. So what is the angle between E and dr? Theta is equal to 0 degree. So cos theta is equal to cos 0 degree is equal to plus 1. So I can write Vp minus V infinity is 0 minus EP dr only. Now what is the electric field at point P? It is KQ upon R square. So V at P is equal to minus KQ upon R square dr. K and Q being constant will be coming out. So we'll be having minus KQ integration 1 by R square dr. Now we need to put the limit. Now we need to put the limit. What would be the limits? We are coming from infinity to P. We are coming from infinity to P. The limit should be what? Infinity to P. Barabar? Okay. And what will be 1 by R square dr integration? It will be minus 1 by R. R to the power minus 2 plus 1. This means what? Integration R to the power minus 2 dr. It will be R to the power minus 2 plus 1 by minus 2 plus 1. R to the power minus 1 by minus 1. That means what? Minus 1 by R. So this will be what? Minus 1 by R, P and infinity. That the minus sign will come out. It will make the entire one as positive. So Vp is equal to KQ 1 upon r. What is the value of r at the point P? What is the value of the distance at the point P? The value of the distance at the point P is what? Smaller. Minus the value of the distance at infinity is infinity. Right? The r is what distance? What is the value of the distance at this point P? First point P, then minus infinity wala case. The value of distance at point P is what? Smaller. The value of infinity at smaller is what? Infinity. So 1 by r minus infinity, 1 by r is 1 by infinity is 0. So v at P, we are having what? As kq upon r. V at P, that means V outside we are having as what? kq upon r. Clear? This is the electric field potential at this point P, which is an outside. It's a beautiful one, right? Yaad rakho, kaam aayega. So let's talk about the surface. At surface, we know at surface, small r is equal to radius. Then surface, what it will be? kq upon capital R. kq upon capital R. This is at the surface. Clear? We are told to find out the P here. We took the other difference point is infinity. We brought a charge from either to either. Now we know how to calculate potential at the point when electric field is given. We know to calculate potential when electric field is given. We know the electric field is here. E is equal to k upon r square. We have to find the potential. Okay, potential calculation. Right. When electric field is given, calculate potential. Potential at P, electric field given, k upon r square. Clear? Okay, now let's get into the inside and the center cases as well. Okay, before getting into the inside case, let me show you the tricks. Say me one thing, when you're having a point charge plus Q at a distance of r, what is the potential here? V is equal to kq upon r. So from a point charge at a distance of r, the potential is kq upon r. From a charged sphere, potential is kq upon r. So can I imagine that the charge is not on the surface of the sphere, rather the charge is at the center of the sphere? Can I consider the charge is not on the surface, rather the charge is where? At the center of the sphere. The charge is where? At the center of the sphere as a point charge. At a distance of r from a point charge, field potential is kq upon r. We are imagining the entire charge to be as a point charge at the center. Distance of r, the field potential is what? kq upon r. The same case we saw in the case of electric field also. In case of this type of sphere, solid, hollow, non-conducting, conducting, whatever is written over there, we can imagine as if the entire charge on the surface is where at the center of the sphere as a point charge. A distance दिया होगा, निकाल लो. Electric field with our electric field potential. Clear? But in exam, if they ask you to derive these things, do not write this concept. Okay, or else they'll come to your home, check the copy in front of you, and will put 00. Now let's talk about the inside case and then eventually to the center case. Inside the sphere, this is my sphere, radius r. Let the inside point be this one. The distance is always calculated from the center. So for inside point, r is less than r. Here we need to calculate the potential. Let this point be P. Let this point be P. So till obviously, I'll be doing We'll be using delta V is equal to minus integration E dot dr. So for calculating delta V is what? V final minus V initial minus E dot dr. What should be the V final? The point we are calculating. We need to bring a charge from the initial to the final. I need potential at the point P. So I need to make V initial infinity again. Right? If it is 0, I can say Vp is equal to something like that. Okay. So which point to be considered as the initial point? We need 2 points, 2 reference points. One is P, where we need to reach final point. Which point to take as the initial point? Infinity. This time we'll be not taking infinity. This time we'll be taking the surface of the sphere as the second reference point. This time we'll be taking the surface of the sphere as the second reference point. Why? Okay, I'll answer it. Not now, after 5-6 minutes later, I'll answer. Let us see, by taking as the surface. Minus V surface is equal to. Which electric field you're talking about? Electric field inside the sphere. Now say me one thing. What is electric field inside the sphere? Electric field inside the sphere, it is a hollow solid conducting. It is always 0. Electric field inside a conducting sphere is always 0. So 0 dot there will giving us what? 0. Again. Right? So Vp is equal to what? Vs. That means what? V inside is equal to what? V surface. And what is what the surface? Surface is equal to Kq upon R. So electric field potential inside the sphere is also the same as Kq upon R. Am I clear? Am I clear? Inside also it is how much it is coming. It is Kq upon R. I can understand that you are having problem with this one. Why we took the reference point this time as surface and not infinity. I'll be coming to that. Don't stick to that point. Stick with this one. Is this calculation clear? Okay. So inside C, okay, fine. Outside it is C. V proportional to 1 by R. Okay, na? K, Q are constant. So outside V will be proportional to what? 1 by R. Surface you can see K, Q, R are all constant. So V is constant on the surface. Inside you can see K, Q, R are all constant. Inside it is also constant. The inside it is constant means what? Inside the sphere, everywhere it is constant. But the center also it will be constant only. Inside, everywhere it is constant. At the center it will be what? Constant, Kq upon. So center one is also how much? Kq upon R. Now coming to answer your question. Why in this case we are not taking infinity as the reference point, rather we are taking the surface of the sphere as the reference point. Say me one thing. What is the electric field outside the sphere? Kq upon R square. Electric field outside is Kq upon R square. Inside it is 0. Inside it is 0. That means what? Outside the field is continuous. There is no breakage in coming in between. There is no obstruction coming in between. Outside it is a continuous field. Non-uniform field, but it's a continuous field. Inside it is also a continuous field. Everywhere it is 0. There is no disturbance. So from the center to the surface, we are having a continuous field. And from surface to the outside, we are having a continuous field. Here we are having a boundary. Remember the cases of electric field. Electric field was maximum on the surface of the sphere, Kq upon R square. Outside it is Kq upon small r square, and inside it is a 0. right? The graph was something like that, if you remember. The graph was something like that. See, inside it is continuous, outside is also continuous. There is a disturbance in the surface. There is a breakage in the field in the surface, right? Outside continuous, inside also continuous. There is a breakage in the surface. Now, it is very much possible to take this second reference point as infinity. It's very much possible. But in that case, what we need to do? We will have to now calculate the work done from infinity to the surface. Then we'll have to calculate the work done from the surface towards the inside any point. And we have to integrate different places. It will be troublesome and then hectic one. Just to overcome all those hassles, we need to choose two reference points. One is the point where I need to calculate the electric field. The other point needs to be chosen wisely. Every time not infinity. If we had chosen infinite over here, we could have done it. Very much we could have done it. It is possible. But here you have to calculate the work done from the infinity to the surface. Then again from the surface to any other inside point, it will become a troublesome. Rather, if we take it at the surface, rather if you take the second reference point, the surface, we're already having a ready-made expression for the electric field potential on the surface. We're using this one, and it can calculate very much easily. If we use this one as infinity also, our expression is going to come in this way. But maybe I need to calculate a very elaborate and detailed one. One of these things, so we are talking about surface as the second reference point. That is the only explanation. Clear? So these cases are already covered. The remaining cases with solid dielectric sphere. Solid dielectric sphere. Outside, surface, inside, and center. Is it visible? Yeah, it is visible. So before getting into these things, let us see a graph. V versus R graph, because of a solid conducting, hollow non-conducting sphere. V versus R graph. Along y-axis V, along axis is R. This is the center. This will denote the surface. Again, this much will denote whatever is happening inside the sphere. And from here to here, we'll be talking whatever is happening outside the sphere. And this part will denote the surface. And this is the center. What is happening at the center? The ink has become very faint. I think everything is visible. Yeah, it is visible. Tell me one thing. Center it is what? Constant. Center it is what? Constant K, constant Q, constant radius, constant. Center constant, inside constant, surface constant, all same value. That means what? You start traveling from the center. You start traveling from the center towards the surface. Everywhere is constant. Up to the surface is constant. The moment you reach the surface, outside it is proportional to 1 by R. Outside it starts decreasing. Right? The graph will be something like that. So traveling from the center to the surface, it is constant. It's constant. And outside the surface, it starts decreasing. Here, V proportional to 1 by R. Yeah, it is constant. Clear? This is the V versus R graph of this case. Solid or hollow conducting and hollow non-conducting is. Now let's get into this one. This will be the last topic. It is 10:12 p.m. I hope you guys are not hungry. This is not even the time for dinner also. You can still have a class of some other 45 minutes. But I'll try to wrap it up in the coming half an hour. बुक करो तुम लोग. So solid dielectric বলে তো non-conducting sphere. And in all these cases, the spheres are how charged? Uniformly charged. Uniformly charged. There is no variable charge distribution. Okay. So let this be the sphere. In case of a non-conducting sphere, this charge resides where? In the volume. The charge resides where? In the volume. The charge resides where? In the volume. Let the radius be r. The first case we'll be talking about outside the sphere. Distance always taken from the center. So let this be the distance. Let this be the point P. Distance P is smaller from the center. For outside point smaller greater than r. Let this point be P. We're asked to find out that the charge is plus Q on the volume of the sphere. We're asked to find the potential at P. The potential at P will be given in the concept of delta V is equal to minus E dot dr. And what is delta V? V final minus V initial is equal to minus E dot dr. What is the direction of the electric field? This is a positively charged sphere. Direction of the electric field will be outward. Direction of the dr. Direction is always taken from the center. R is always from the center. So dr will be directed in this way. So E and dr, same direction. Theta is equal to 0 degree. So we'll be having V final minus V initial is equal to only and only E dr, because cos theta is equal to 1. Theta is equal to 0 degree. What will be the V final? Obviously, we'll be taking about another reference point. In this time, the reference point we're talking about is infinity. We'll be bringing a point charge or a distance from infinity to P. The initial point is infinity, final point is P. Minus integration E dr. Say me one thing, what is the electric field outside a sphere? What is the electric field outside a solid non-conducting sphere? I gave you the tricks. Electric field outside any kind of sphere. Electric field outside any kind of sphere. KQ upon distance square. Whatever the sphere is, consider the charge at the center, right? So it will be KQ upon r square dr. What about the limits? We are bringing the charge from infinity to P. The limits will be infinity to P. We are asked to find out the potential at P, Vp. V at infinity is 0. KQ being constant will be coming out minus KQ. We'll be having infinity to P 1 by r square dr. And 1 by r square dr is minus 1 by r. So this will be Vp is equal to minus KQ minus 1 by r P and infinity. Okay, yeah, let's see. So Vp is equal to minus will be plus KQ. The distance of the value of r at a distance of P is smaller minus the distance of, the value of r at distance of infinity is infinity. So it is coming as what? 1 by infinity is 0. 1 by infinity is 0. So V outside will be coming as KQ upon R. V outside will be coming as KQ upon R. KQ being constant, I can say outside V proportional to 1 by R. KQ is constant, so V proportional to 1 by R. That means what? For a solid dielectric non-conducting sphere also, I can what? I can imagine the entire charge to be concentrated at the center of the sphere as a point charge plus Q, because we know from a plus Q point charge our distance में potential is KQ upon R. Same expression. So I can consider the entire charge distributed in the volume is actually located at the center of the sphere as point charge. Clear? So similarly for the surface, we can write at surface small r is equal to capital R. So V surface is equal to KQ upon capital R. Surface it will be KQ upon capital R. KQ are all constant. So surface V is what? Constant. For surface, V is what? Constant. I hope it is clear for all. And there should not be any kind of doubt. Barabar? Let me have some water. Dekho. I'll be getting into the insert case. Now talking about the inside case. Inside case. For inside, small r will be less than r. Let this be the inside point P. Small r is less than r. If you remember the case of solid dielectric sphere, electric field, this was the only case. The formula, the expression came out to be different. KQ small r upon capital R cube. I showed you to remember how to remember KQ upon capital R square into small r by capital R. KQ upon capital R square is the electric field on the surface multiplied by small r upon capital R. Okay. So inside case, in case of a dielectric solid, always creates a trouble. Let us see what happens here. It's a beautiful one, not trouble. Say, trust me. So inside point P, we'll be writing what? Delta V is equal to minus integration E dot dr. And delta V is V final minus V initial is equal to minus E dot dr. And V final is the point where you're calculating the potential V at P. And initial points, what to take? In the last case, you have seen that in the inside cases, we take the initial point as the what? Surface. We do not take the initial point as infinity to avoid any kind of hassle. So we're taking the initial reference point as surface. And what about E dot dr? As because the volume is uniformly charged, we imagine that the electric field is outside. In this way, the direction of dr will be, as because the distance is always taken from the center, direction of dr will be also this. So dr and E are all in the same direction. Theta is equal to 0 degree. So we'll be writing only and only E dr. Theta is equal to 0 degree. That makes what? Cos theta is equal to 1. And what is this electric field? We are talking about the potential at P. Considering the inside case, this will be the electric field inside a solid dielectric field. So what is the potential at the surface? Potential of the surface is KQ upon capital. What is the electric field inside? Electric field inside a solid dielectric is KQ R upon R cube. Right? So it will be KQ R upon R cube dr. Barabar? So what about the limits? What about the limits? What about the limits? You're taking the second reference point as what? Surface. You're taking the second reference point, initial point is what? Surface. We bring the charge from the initial point to the final point. Final point is P inside. Initial point is surface. So you are beginning the journey from surface and you are reaching to the point P. Okay, initial point, final point, surface to P, surface to inside point. The limits will be surface to the inside point P. So Vp minus KQ upon R is equal to integration surface inside point P. Okay. Now say me one thing, KQ upon KQ upon R cube are all constant inside R dr, surface and the inside point P. What is the integration of R square by 2? Integration of R to the power 1 by 1 by 1 by 1 R square by 2. बराबर. What is the value of the distance? Can I bring 2 outside? Let me bring 2 outside. It will be 2R cube. So inside we'll be having only R square and limit says P and S. So what is the value of, first we'll put the distance value at P, then distance value at surface. So what is the value of distance, what is the value of P? Sorry, what is the value of the distance at the point P? The value of the distance at the point P is what? Smaller, right? So Vp minus KQ upon R is equal to KQ upon 2R cube. The value of the distance at the point P is smaller, minus the value of the distance of the surface from the center is capital R radius. My marker is crying. Chhod do. Is this part visible? I guess this part is visible. Yes, because one of you let me note in now. I am taking into consideration that this part is visible. Let me come to this part. We come to this side. Ting, 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 ting. Simple calculation only, nothing complex. Vp minus KQ upon R is equal to, just multiply. It will be what? KQ R square by 2R cube minus, it will be, multiply this one by R square. R square will be eating 1R. KQ upon 2R. Now bring this minus KQ upon to that side. It will be plus KQ upon R. Or this side it was minus KQ upon R. On changing the side, it will go there. It will be minus plus KQ upon R. Na? B at P is equal to. Calculate this one. What will be that? KQ R square by 2R cube. On calculation, what it will be? What it will be? Let me try to do in this way. That it will be minus, here it will be 2, here it will be 2, something like that. Right? कोई गलती हुआ? Any mistake? Any mistake? Or have I made it complicated? I guess I've made it complicated. Okay. Yeah. Vp is equal to, multiply this part, it will be KQ small r square upon 2R cube minus, multiply this one, it will be KQ upon 2R. And I'll be bringing this one to that side. It will be plus KQ upon R. Again, oh. There was a negative sign, right? There was a negative sign. Where did this negative sign going, my brother? तभी तो negative sign, negative sign. So this one will be negative. Negative, this will be only positive. And this one will go to the that side, V positive. Notice all now everything is perfect. So V at P is equal to, this will be giving us what? This will be giving us KQ R square upon 2R cube. And this will be giving us 3 by, right? KQ upon 2R plus KQ upon R. What it will be? 3 KQ upon 2R, na? Are, 3 na. Now take the LCM as 2R, 2 KQ plus KQ, 3 KQ upon 2. Now let me take common from here as KQ upon R. Is there still any kind of mistake in the expression? Yes, this is my negative. This marker is not working. It's my mistake. This is negative. So let me take common from here, KQ upon R, and the expression will be 3 by 2 minus KR square upon 2R square. This is the expression. This is the expression inside the sphere at this point P. I did the blunder is that my marker is so fade now, I just overlook this negative side. And that made the blunder. It's my mistake. Clear? Check the calculation at your own at home. This is all correct only. So inside you're having something like that. See, the inside cases always trouble. In inside you're having something like that. KQ upon R 3 by 2 minus KR square by 2R square. Now tell me one thing, what will be happening at the center? For center, R is equal to what? 0. Just keep your R is equal to 0. Just keep your R is equal to 0. The entire part will be 0. So V at center will be what? Is it visible? I'm writing here. V at center will be what? If you keep smaller is equal to 0, this entire part will be 0. That means will be remaining behind with 3 KQ upon twice of R. Now, what is KQ upon R? KQ upon R is potential at the surface. KQ upon R is potential at the surface. That means what? At center, 3 by 2 is 1.5. At KQ upon R is on potential on the surface. That means what? At center, the potential is 1.5 times greater than the potential at the surface. At center, for center, if smaller is equal to 0, if smaller is equal to 0, the entire one becomes 0. The V at center will be KQ upon R into 3 by 2, KQ upon R into 3 by 2. 3 by 2 is 1.5, KQ upon R is potential on the surface. That means for at center, the potential is 1.5 times greater than the potential at the surface. 1.5 into potential at the surface, it is 3 by 2 into KQ upon R. Clear? So it means one thing, inside how potential is varying with R, smaller potential is varying how much with the distance. The KQ upon R is constant, 3 by 2 is constant, K constant, 2R square is constant. So definitely inside potential is varying proportionally, almost proportionally with r square, v proportional to r square. And center, it is 1.5 times of the potential of the surface. Surface, it is constant, the center is also constant. Center is also constant because 3 pi 2 is constant. So Vs constant. So center is also constant. You need to remember these steps. They can ask you in the question. So now let us see the graph diagram. Let's see the graph diagram. This is the sphere. Tell me one thing. Inside, it is actually b proportional to minus r square, right? 3 by 2 minus k r square upon 2 r square. 3 by 2 constant k constant 2 r square. Inside, it is actually proportional to minus r square. Now my marker is not giving this minus sign. Gajab bejati. Now marker is acting like a duster. I'm trying to give the minus sign, it is erasing it more. Gajab bejati. Chalo aage. Chalo, let's see the graph. This is the center. Right? Tell me one thing. Center, it is at center, it is 3 by 2 k upon r. At the surface, it is kq upon r. That means what? You're traveling from the center to the surface. Center, it is what? At center, it is 1.5 times of the surface. Center, it is more, surface, it is less. Center, it is 1.5 times more than the surface. Surface, it is 1.5 times less than that of the surface. Surface, it is 1.5 times less than that of the center. That means what? You're traveling from center to the surface. Potential is decreasing. Surface, it is 1.5 times less. Center, it is 1.5 times more than the surface. Right? Center from the surface, it is decreasing. Right? So now let us see the graph. At the surface, it is constant. Outside, it is decreasing. Inside, it is proportional to minus 1 by minus r square. Center, it is constant, and from center to surface, it is decreasing. So from center to surface, it is decreasing. Center to surface, it is decreasing. There is a v, this is r. This is v proportional to minus r square. From center to surface, it is decreasing. Surface, it is constant. And outside, v proportional to 1 by r. Clear? So many messages. Anyways, center, it is 1.5 times more than that of the surface. Surface, it is less than the center. And from the surface to the center, inside, you can see that it is proportional to minus r square. It is proportional to minus r square. At the surface, it is having a constant value. And outside, it is decreasing at the rate of 1 by r. This is inside, and this is outside. And this is surface. Clear? And center is what? 1.5 times. This is 1.3. If this is at the surface, if this is at the surface, center is 1.5 times more. Let this distance be 1. So this distance is visibly more than 1.5. Okay, now? At the center, it is at the center, the value of v is 1.5 times more than the value of the surface. This is the value of v at the surface. Center, it is 1.5 times more. This length is greater than this length. Clear? Okay. This is all about the sphere cases. Now let's try to have a beautiful summary. Let's try to have a beautiful summary. What summary? This summary will be comprising both electric field as well as the potential also. Say me one thing, outside any sphere, outside any sphere, electric field is equal to KQ upon R square. Potential KQ upon R. Barabar? Inside any sphere except dielectric solid. And this one, except dielectric solid. Inside, what is the field? Inside anywhere, electric field is always 0. And potential is always KQ upon R. Sorry, KQ upon capital R. Barabar? Outside and inside. And in case of a solid dielectric, inside electric field is KQR upon R cube, and potential is KQR into 3 by 2 minus KR square by 2R square. And for center, we'll be following the inside case. Just put R is equal to 0 for center. And for surface case, use the outside case. Just keep R is equal to capital R for surface cases. How many values there have been? 1, 2, 3, 4, 5, 6. All the cases of spheres, 16 cases, electric field, 16 cases, potential, 32 cases summarized here. Outside any sphere, electric field KQ upon R square, potential KQ upon R, any sphere. Inside any sphere except dielectric solid. This is the one which does not on P every time. Inside any field, inside any sphere except dielectric solid is equal to 0, potential KQ upon R. For center, put radius is equal to, put R is equal to 0. For surface, put R is equal to capital R for radius. And inside the solid dielectric, P is equal to KQ R upon R cube, and P is equal to KQ upon R into 3 by 2 minus KR square by 2R square. Clear? Okay. So this is all about today's class. We'll be seeing a very small numerical and we'll be wrapping up the class. And the numerical will be from the field and potential relation. Numerical will be from the field and potential relation. Just give me 5 minutes. Sorry, just give me 2 minutes, not 5 minutes. Just give me 2 minutes. Yeah. The charge of my battery was almost coming to an end. So I had to put it in charge. We'll be just doing one numerical and wrapping the class for today over here. Suppose we are given the value of V is 2x minus y plus z in a 3D area. What is the meaning of a 3D area? 3D area means an open space. Okay. We are asked to find out electric field vector and its magnitude at a point 1, 0, 1. That means what? At somewhere we are given the field value as V is equal to 2x minus y plus z. We are asked to find out the value of the electric field at any point in this field, and the coordinate of the point is 1, 0, 1. That is what? We need to calculate V. Delta V is equal to minus E dot dr. We need to calculate what? Electric field. V given, we need to calculate electric field. If E was given, calculation V is easy. We need to calculate the electric field. Remember this formula, that derivation. Okay, let us see that example. What is Ex? What is E? E is nothing but Ex I cap, E y j cap, E z k cap. That is our electric field vector. Now, if I can find out Ex, Ey, and Ez, I can aramse calculate the electric field. And what is Ex? What is Ex? Ex is equal to minus del V del x. That means what? I need to partially differentiate V with respect to x to calculate Ex, with respect to y to calculate Ey, with respect to z to calculate Ez, right? So what will be the partial differentiation of V with respect to x? We'll be differentiating this one. Y and z will appear as constant. Their differentiation will be 0. The partial differentiation of 2x is what? Only 2. Partial differentiation of 2x will give us what? 2. And y will appear as a constant, z will appear as a constant. So the Ex is equal to only and only 2. Clear? Okay, minus 2. No? That is the minus sign. Now if tell about Uy, minus del V del y. What will we get if we differentiate minus y? If we differentiate minus y, we'll be having what? Plus 1. If you differentiate minus y, what will be happening? You add dy, dx, dx1, dy, dy1. So dy of minus y give us minus 1. There is already a minus sign before, minus minus plus 1. And this will appear as 0, this will appear as 0. Barabar? So similarly, Ez is equal to minus del V del z. This will 0, this will be giving us 0. And partial differentiation of z with respect to z will give us what? 1. That is minus 1. So we'll be writing minus 1. Whatever. So already having the value of Ex, Ey, and Ez. So what is our E vector? E vector is equal to Ex is to minus 2 I cap plus what is Ey? Ey is plus 1 j cap. That means only j cap. And Ez is minus 1. Minus 1 k cap means what? Only k cap. This is the value of electric field vector. This is the value of electric field vector. So what would be the magnitude of the electric field? Magnitude is given as minus 2 square plus 1 square plus minus 1 square. 4 plus 1 is equal to under root 6. And what is the value? What is the unit of electric field? Newton per coulomb, or also we can write volt per meter. Okay, this is a simple case that we will be given, we have to calculate it. We'll be seeing lots of such examples in upcoming classes. We'll be having a particular numerical class. We'll be having some 30, 40 beautiful expressions. The next class will be on equipotential surface. Basically, it is a topic of 15 minutes only, equipotential surface, but we'll be having a very much in-depth understanding of equipotential surface. We'll be talking about each and every concept of the equipotential surface. It is going to be a very much theory class, no derivation, no numerical. The class will be short one also. Okay. So this is all about today's class. We have seen the relation between electric field and electric field potential, field being uniform and non-uniform, and all the sphere cases, solid conducting, hollow conducting, so then solid non-conducting, hollow non-conducting, inside outside surface, and the 16 cases. And after that, we saw a beautiful summary that summarizes all the 16 plus 16, 32 cases of electric field and the potential related to the spheres. All cases come, and a small very numerical, where we got our idea clear that what will be doing to calculate T when V is given. Please go through all the derivations, all the expressions, all those things, study them very much carefully and attend the next class. This is all about today's class. Thank you. Good night. All the very best.